Hello again, 3C students. Fallstad.com is one of my favorite websites for physics simulations. I'm very fond of this website. We will be using this several times this semester. Starting right now, here's a nice visualization of a single source of what looks like sinusoidal waves. You can tell that the wavelength, can I pause this? The wavelength, which is the distance between these crests here, it's like you're looking down on ripples in a pond. If you could look at it from within the surface of the water, it would look much like a sine wave. The surface of the water would look like a sine wave. Of course, this doesn't have to be water waves. This could be longitudinal waves in air. But the bright spots you can think of as the crests of the wave, and the dark spots are like the troughs. So the wavelength is pretty apparent there. And because the wavelength is obviously constant in time, and the speed of the wave also appears to be constant, that means the frequency is constant. So here's a single source of constant frequency waves. And later we'll take a look at two sources, and we'll talk about this very common wave phenomenon called interference. We'll talk about the famous double slit experiment, which plays a pretty central role in our very introductory look at the Schrodinger. Well, we probably won't get to the Schrodinger equation, but we will talk briefly about some bizarre quantum behavior and the Doppler effect. Chapter 16 includes a discussion of the Doppler effect, and we will also use this simulation to investigate that phenomenon. Where can I find that in here? Here we go, Doppler effect number 1. Okay, that's just a teaser. We'll come back to that later. Right now, we're just here to talk about the definition of this quantity called intensity, the intensity of a wave. So we'll start with two-dimensional waves. Here's a great example of two-dimensional waves that you're familiar with. This could be formed by throwing a pebble into the pond, or maybe there's a little duck just under the surface flapping his wings. This is a screenshot from the simulation we just looked at. And as I pointed out, you can measure the wavelength as the distance between the centers of two adjacent bright fringes. I'll call these fringes because later when we talk about the interference between laser waves, we will use that word fringes. Or you could measure it from the center of a dark fringe to the center of an adjacent dark fringe. And let's use this yellow circle to represent a quantity of energy that's moving outwards from the source. If this is a source of sound waves, then you're talking about the mechanical energy of the oscillating air particles. If it were an electromagnetic wave, the source would be something like an antenna. And I'll use the thickness of the ring to signify or represent how concentrated perhaps the energy is. And let's use, for now, the symbol E0 for the energy emitted by the source. So this 0 for me means the source, and that's the quantity of energy that is emitted per unit time. If these were mechanical waves on the surface of that pond, I mentioned the little ducky, obviously the duck has to expend energy to flap its wings. Where does that energy go? It ripples outwards. So waves carry away energy. And as time advances, of course, that circular wave front will move outwards, and I'm making it thinner as it goes outwards, again, to represent the fact that the energy becomes less concentrated, so to speak, because at the beginning, all that energy is gathered within this small circle, and then a few seconds later, it's spread out over a much larger circle. So obviously, it's got to be more diffuse, less concentrated. So let's look at just a short segment of that circular wavefront, and I'll call it delta S because in math classes, we often use the letter S for arc length. So here's a short arc length. And of course, the length of these red radii, well, that's the radius of the wavefront, which is increasing with time as that wavefront moves outward. Now, if this little ducky was flapping its wings repeatedly, then by the time this wavefront has reached this size, the ducky has already emitted several more wave fronts, but we're tracking the progress of just one of those wavefronts, which in this picture was emitted at some earlier time. Now, this energy, E0 or E naught, while it was originally clustered around the source, now it's spread all around this circle. And let's use E delta S to denote just the fraction of that energy that passes through this arc length, which is obviously only a small percentage of the total energy. So clearly E delta S is much less than E naught. Only some of that original energy released by the source intercepts this very short arc length. And here's a very reasonable statement of proportionality that you should think about. Would you agree that the energy which passes through this little arc length compared to the total energy on that wavefront should be the same as the ratio of this arc length to the circumference of the circle? What could be more intuitive than that, right? It's just a simple statement of proportionality. For instance, if this arc length is 1/20th as long as the circumference, then it seems pretty clear that 1/20th of the energy which is radiating outwards will pass through this piece of the circle. That's all this says, because delta S is the arc length and 2 pi r, as you recall, is the circumference. We can rearrange that by putting E naught on the other side, and I will go ahead and enclose this ratio in parentheses. And what can we do with that? Well, I guess I'm more interested in the next step. So now I'll take delta S and put it in the denominator over here. And this is really the end result that I was looking for. Just to remind you, E naught was the energy emitted by the source per unit time. I said something like 1 second. So in the SI system, that's the unit of time. And E delta S is the quantity of energy that passes just through that arc length. So let me remind you, because hopefully you're already thinking, wait a minute, energy per unit time. If I'm saying the energy per time, maybe there's a word for that type of quantity. So the definition of power, really average power, is the total quantity of energy exchanged or produced or used, whatever the transformation you're talking about is. Take that total quantity of energy, divide it by the time during which that transformation happens, and that ratio is what we call the power, the average power associated with that energy transformation. So if you look at your electric bill, for instance, you may find that your average daily consumption of electrical energy is something like 15 kilowatt hours. That's a unit of energy. So the power, which is the rate at which you're using electrical energy, would be 15 kilowatts per day. Now, those are not SI units, but that's a totally valid unit of power. Or maybe you like to go jogging and you somehow determine that you're burning 300 food calories per hour. That's another measurement of power, 300 calories per hour. Again, not SI units. The SI unit would be the joule per second. If you're producing or exchanging or using 1 joule of energy per second, that's a power of 1 watt. And by human standards, that's actually a pretty small power. I just looked this up today. Your heart actually does mechanical work at a rate of about 2 watts, 1 or 2 watts. And your entire body, if you're running upstairs or wrestling or some other high intensity activity, you could easily be putting out 1,000 watts, especially if you're a larger person. If we take this equation and solve it for delta E, we get this. If you multiply your rate of energy consumption or power by how long you do that for, that will give you the total energy that you've consumed. So I just mentioned, the kilowatt hour as a unit of energy. This is one of my favorite units. There's something so amusing to me about the fact that if we say, if you're consuming energy at a rate of 1 kilowatt, which is 1,000 joules per second, and you do that for 1 hour, let's just call that unit of energy a kilowatt hour. I mean, even in the name of the unit, we see the product of power, which is the kilowatt, and time, which is the hour. Okay, so really what I've been talking about, I I not hypothesized, I just assumed that this source was putting out E naught units of energy per second, so per unit time. That's really the power that I'm talking about. So if it was 5 joules per second, then rather than calling that 5 joules of energy, I can just say the rate of energy consumption is 5 watts. So let's replace this capital E with the P for power. So P naught will be the number of joules per second emitted by the source. And then P delta S is the number of joules per second passing only through this small segment of the circular wavefront out at this distance, R. And let's think about this quantity on the left. Well, I guess what I'm doing right now is highlighting in red the quantities that will change as the circular wavefront gets bigger, or if we go back in time as it gets smaller. So let's go back in time and you'll see that R is much smaller, right? The radius here is much smaller than it was in the previous slide. And if the denominator gets smaller, then this whole quantity gets bigger, right? Smaller denominator, bigger fraction. Well, over here, you'll notice delta S hasn't changed. So I'm still considering how much energy passes through this segment of arc. Maybe it's a couple inches across, but the idea is it's the same arc length as it was before, but now it's closer to the source. So the only way for these two quantities on the left and right to be equal, if the one on the right has increased, is if the numerator over here increases, because I didn't change the arc length. So the amount of energy passing through this piece of arc per second, in other words, the power, is now considerably greater than it was. And that's because we're closer to the source. This is all intuitive, right? You all know this, but we're trying to express it mathematically using proportionality, and we're trying to come up with an actual formula that we can use to do calculations. Everybody knows if you step away from a bonfire or campfire, you feel less heat, so to speak, hitting your face. Later, we're going to talk about the fact that that quote heat is really infrared radiation. It's like light that has a color you can't see. It's beyond red. But the closer you are to the campfire, the more intense that heat is. Same with a speaker. If you're at like a club with a really loud speaker system, you can't stand too close to it or you'll definitely damage your ears. As you get farther from the speakers, the sound is less intense because as the waves radiate outwards, the energy is distributed over a greater region in space, I'll say. So let's take a numerical example. Sometimes things really click when you just look at an example with numbers. Let's say that the speaker, no, not the speaker. Let's say that, and I really should have gone back to the other picture, but let's say there's 50 joules passing through this arc segment or arc length every second. Every second, 50 joules pass through just the red arc length. And of course, that means that more than 50 joules are being emitted by the source every second because the rest of the energy goes out in these other directions. So the 50 joules per second is just the amount that's passing through this arc length. And suppose that that arc length is 1/4 of a meter, so 25 centimeters. What is this ratio? 50 joules per second passing through an arc length of 25 centimeters. You just plug those numbers into the calculator or do it in your head. We're dividing by 1/4, which is multiplying by 4. That's the same as 200 joules per second per meter. So that tells us that if the arc length were not 0.25 meters, but a full meter, which would take us farther around the circle, 200 joules per second would be passing through that arc length. So this, hopefully, it's kind of intuitive for you that this fraction tells us about how concentrated the power is. I'm getting ahead of myself here. Let me just re-express that one more time. So for each meter of arc around that circle, 200 joules of energy flow past every second. I'm being really precise here in distinguishing power from energy. So when I say joules of energy and then over here per second, that's really the unit of power. So you could think of that as how concentrated the power is. Now, let me go back here. If we went back to the previous picture, so way out here, I've still got my 0.25 meters of arc length if I stick with the same delta S, but it's very clear that the amount of power passing through this arc length now is less than it was before, because most of it's going through the rest of the circle. So now the numerator would be smaller, but the denominator would be the same. That would give us a number quite a bit less than 200 watts per meter. So the power would be less concentrated in space out at this distance from the source. And maybe you're thinking, why don't you just call it intensity? I'm trying to avoid that word because usually we use intensity when we're talking about waves in three-dimensional space, but that's basically what I'm describing here. The power concentration means more or less the same thing as intensity. And if you look at the statement of proportionality that we set up, you can see here that this left side is the power concentration because it's the amount of power per unit distance. And evidently, it's equal to this. This is how you calculate it. All you have to do is take the total power being emitted by the source and divide that by the circumference of the circle, which makes sense, right? You've got a certain number of joules per second flowing outwards. It's distributed all around that circular wavefront. So you just divide by the circumference, the total length around that, or the total distance around that circular wavefront to find the amount of power per unit distance. That's it. You probably could have just guessed this formula without going through my argument about statements of proportionality. Well, in this class, much more often, in fact, I don't think we're ever really going to talk about two-dimensional waves. We're talking about waves in three-dimensional space. Cough break, hang on a second. Okay, so first of all, what's with this fancy word isotropic? That just means that your source of energy, your source of waves, sends out power with equal strength in all directions. It's not like it focuses the power in one direction or another. And it's actually difficult to find isotropic radiators. Well, I shouldn't say it's difficult, but they're less common than the opposite, which is radiators that tend to focus their power in some directions over others. But a good example would be a light bulb. It doesn't matter where you are in the room. If it's an incandescent bulb like this, you see the light with basically equal intensity as long as you're at, at the same distance. It doesn't really matter where you are in the room. Maybe the best example would be a star, because stars are spherical, and for the most part, they have the same intensity of light coming off their surfaces at every point on the surface. Now, that's only true as long as you don't get too close. Nowadays, you can pull up these incredible images of the sun and see that when you get close, it is more detailed than that. There are regions that put out more. There's this granulation, and then there's sunspots. And so if you haven't spent any time looking at some of these incredible pictures of the sun, it's probably been 10 years now since the Solar Dynamics Observatory has been putting out these amazing pictures. I should just show you one right now, huh? Anyway, too many detours. Here's a graphic showing spherical wavefronts moving outward from a source. So it's like an old-fashioned cutaway here. The distance between one wavefront and the next, that's the wavelength. And this could represent, again, sound waves, light waves, seismic waves deep within the earth, perhaps. Let me say one more thing about this word radiator. It's not the radiator in your car, and it has nothing to do with radioactivity or radiation poisoning. It just means something that emits energy in all directions. In other words, the energy radiates, as in radius, away from the center. That's all that means. A good example of a non-isotropic radiator would be various types of radio antennas. And that shouldn't surprise you, because imagine if this antenna tower, I think there are multiple antennas mounted on this tower. Imagine if all those antennas emitted energy equally in all directions. Why would you want to send energy straight up away from the earth? Who's living directly above an antenna tower? So that would be wasted energy. You would prefer to have energy radiated in some directions and not others. So many of you, depending on what discipline you go into, will be familiar with these gain diagrams. In fact, even the microphone that I'm speaking into right now, obviously the microphone receives sound waves. It doesn't emit, or excuse me, it does not emit sound waves. But when I read the brief manual for the mic, the setting I'm using right now is supposed to have a cardioid pattern, meaning heart-shaped. So there are certain directions around the mic where the microphone is more sensitive to sound waves. So the microphone would not be isotropic. In fact, every time I pause and come back, you've probably noticed that sometimes the quality of my voice sounds different. And it's probably because I just shifted in my chair, or I'm sitting in a slightly different position. And so the way the microphone is picking up my voice has changed. So that would be a non-isotropic receiver, I suppose. Another great example is sound waves emanating from a person's head. Obviously, when you stand behind somebody, you don't hear them as well as when you stand right in front of them. Okay, this is a classic graphic that will help you understand how intensity depends on position in 2 dimensions. So this is supposed to be an isotropic radiator. Power is going out equally in all directions, but let's focus our attention on just the energy that's flowing out between these 4 rays. See this like pyramid shaped angle in 3 dimensions. By the way, there's something called a solid angle that you may not be familiar with. If you draw 2 rays on a piece of paper, that's just a regular old angle, if the rays come from the same vertex. But in 3 dimensions, you have to use more than 2 rays to represent kind of like a cone angle in space, and that's called a solid angle. And I'm just going to throw this out there. We don't need this fact, but you know how the circumference is 2 pi? 2 pi radians will take you once around a circle. Well, the total solid angle in all 3 directions is 4 pi. And instead of calling them radians, they're called steradians. Most people don't learn this anymore in high school, but that's why that 4 pi is out front of r squared. The circumference of a circle is 2 pi times r. The surface area of a sphere is 4 pi times r squared. And that's because, well, it's related to the fact that the total solid angle in space is 4 pi steradians. Okay, so when that energy which flows out between these 4 rays, when it reaches the radius r here, that power is distributed over just 1 square here of area A. But when it gets to double that distance from the source, out at distance 2r, you can see that the cross-sectional area is now 4 squares, 4a. So if you've got the same power distributed over 4 times as much area, then of course the intensity has now dropped by a factor of 4. And they're showing you that right here, I over 4. So going twice as far from the source means 1/4 the intensity. When you get out to 3 times the original distance from the source, now you've got your power distributed over 3 times 3 or 9 squares. So the intensity is 1/9 of what it was. That's a very simple rule. Twice as far, 1/4 the intensity. 3 times as far, 1/9. You see how that works? You just take the ratio of the distances and square it. That is called the inverse square law. You're already familiar with it, right? Because it works for gravity as well. But right now we're using it to calculate how the intensity of a wave or a disturbance radiating isotropically from a source, how that intensity depends on distance. So let's do the same thing now that we did previously around the circle. Let's use the symbol P naught for the energy per second being released by the source. And then P delta A will be the power or the energy per second intercepting or just flowing out through this 1 square. So I guess right now forget about this other junk now, just focus on radius R. So P delta A, I'm calling it delta A to be consistent with before when I called it delta S. They're just calling it A, but for me, this is delta A. And does it seem reasonable that the power flowing through just this 1 square compared to the total power flowing through this imaginary sphere in space, that ratio is, of course, just equal to the area of that patch compared to the total surface area. It's much like the statement in the previous slides where I related the power flowing through that one piece of arc length compared to the total power. I related that to just the arc length compared to the circumference. It's the same thing that I'm doing here, just setting up a very obvious statement of proportionality. So let's move some stuff around here in this equation. I've taken the delta A and put it down here. And what are we talking about here? The amount of power flowing through that patch divided by the area of that patch. That's a lot like in the previous slides where I had the power compared to the arc length. This is how concentrated the power is. So just to harken back to the numbers I used previously, I said something like 50 watts were flowing through an arc length of 0.25 meters, and that came out to be 200 watts per meter. We're doing the same thing here, except now, instead of an arc length, we're talking about a little patch of area. So we're talking about how many joules per second are concentrated in how many square meters. So the units here are no longer watts per meter. Now it's watts per square meter. And yes, that's a concentration of power, but now it's okay to use that word intensity. So from now on, I think the whole semester, anytime we use the word intensity in this class, we're talking about a quantity which has dimensions of watts per square meter. And don't forget that really means joules per second per square meter. That's how many joules flow every second through that area of A square meters. And that quantity evidently is equal to the total power coming out of the source divided by the surface area of that imaginary sphere. Makes sense, right? When I go back here, whatever energy is currently passing through this sphere, well, originally it was released by the source. And the number of joules per second, that's this quantity. So as it passes through that surface at radius r, this is the concentration of that power. And of course, as you go out to greater distances, as r gets bigger, the denominator gets bigger, the intensity decreases. It's an inverse square law dependence, which drops off pretty rapidly. I don't have a graph, unfortunately, but 1 over r squared, if you were to graph that, it drops down pretty quickly. And that's why if you're standing near a campfire close enough that it's almost uncomfortable, like you're getting close to burning your skin, well, that would be too close. When you step back a couple feet, it changes very rapidly. You don't have to walk 20 feet away before you feel the difference. Okay, let's use this in an example. Here's the sun, and this picture is a little misleading because as I was just reading today, if you were looking at the sun in outer space, not from within our atmosphere, it's really kind of whitish. The sun looks more white than anything. Here's planet Earth, and I was careful to put Earth in the appropriate phase. If the sun was really over here, then only the left half of the Earth would be illuminated. I was watching The Mandalorian the other day, and they had a cool graphic of the surface of a planet. I forget which planet it was, Endor or something. And then there was a moon above the planet, and the moon was in this phase right here. So the moon was only illuminated on one half, and the sun was way over here. But the planet that they showed just beneath the camera was completely illuminated. And that didn't make any sense, because if the sun's way over here and the moon is only half lit, then the planet should also be half lit. See, astronomy can ruin you for some of your favorite science fiction shows and movies. I'll see if I can find a screenshot of that episode and put that in a future presentation. Okay, so the Earth is 150 million kilometers roughly from the sun, and we just call that distance 1 astronomical unit. That distance was not known until 1768, I believe, and there's a very interesting story behind that. In astronomy, they use the word luminosity to mean the total power of the sun, the number of joules per second coming out of the sun. It is an insane number. Every second, the sun releases 4 with 26 zeros after it joules. And this is going to sound, again, like science fiction to you. You'll have trouble believing this, but in order to release that much energy, it has to convert mass into pure energy. It just takes matter, basically makes it disappear through the hydrogen fusion process, and you get energy instead. And the amount of mass we're talking about, it's like you're your apartment building or your home, plus like every other home on the block, all of those just poof, gone every second. I forget how many thousands of tons or hundreds of thousands of tons. You could look that number up, but it's an unimaginable quantity of mass that is just vaporized, so to speak, every second. It's not really vaporized because even vapor is still there. It's something you could touch and weigh. It's just gone. It's become light energy. And it takes something like, oh, I've already forgotten this number. I think it's 8 minutes. It takes 8 minutes to get from the surface of the sun to the earth. But that's a different topic. Okay, so knowing that, can we figure out the intensity of that sunlight when it reaches the earth, given this distance? And over here in the corner, I'm just reminding you that this is not to scale. The earth is way smaller than the sun in diameter. It's also much further away. Like if we were going to do this to scale, the earth would have to be much smaller and it would be way off the screen, like maybe 20 screens away. Okay, solar irradiance is the fancy word that people use when they're talking about the intensity of sunlight. It's got the same dimensions as intensity. And I've just put this circle here to help you imagine that spherical wavefront. So all of the power flowing through this wavefront originally was released by the sun 8 minutes prior. It's just a simple application of the formula. Take the total power of the sun. That's how many joules per second are released from the surface of the sun. That's how many joules per second have to pass through this ginormous spherical wavefront at the distance of the Earth. Of course, that power is now spread out over a much larger sphere, so it will be much less intense. I'm plugging in that number. Now 150 million kilometers, you'll recall. Million is 10 to the 6th, and I have 3 more zeros because I said kilometers, and we need to use SI units. If you want your answer to come out in watts per square meter, you must plug in watts and square meters. And here's a very familiar number, 1.4 kilowatts. Oh, I left out the square meters. That's look at me. I'm telling you to be observant of your units and I dropped them. So let me fix this. Much better. So I don't have a graphic for this, but if you were to go out, and this is really for the top of the atmosphere, because some of that intensity or some of that light energy is absorbed and scattered by the atmosphere before it ever reaches the surface of the Earth. So by the time you get to the Earth's surface, you're talking more like 1.0 kilowatts per square meter. And that means if you live especially near the equator and you go out in the middle of the day when the sun is high overhead and you draw let's say you have a piece of chalk and you draw on the asphalt a square 1 meter by 1 meter, so 3 feet by 3 feet roughly. Every second, 1,000 joules of energy, sunlight energy, are striking the surface within that square. And that's an easy number to memorize because it's about the same as the power of a microwave. If you're defrosting or if you're cooking a Hot Pocket, I always like to use that example, you probably got the power setting on high, and that draws, a typical microwave oven draws something like 1 kilowatt, 1.5 kilowatts. You can check that, just open up the door and I think it'll give you that number. More precisely, it's 1361. Again, that's above the atmosphere. And I'll let you read this if you're interested. But I was showing you this so that you know that this calculation was legitimate. We got 1.4 kilowatts, and that's pretty darn close to the Wikipedia value. And Wikipedia would never lie to you. Last example here. No, second to last example. The penultimate example. Using an SAT word there. If you haven't taken astronomy, we've got several sections here at Long Beach City College. It's an awesome subject, especially after you've taken 3C, because so many of the concepts that you see, at least in the curriculum that I'm using, is applied in astronomy. You're really well equipped to understand a lot of modern astronomy after you've studied some modern physics. So a whole lot is known about stars. This graphical tool here is called an HR diagram, named after a couple astronomers. And it's basically a catalog of stars that relates their diameters to their masses, to their brightness, to their temperature. And basically, I keep saying basically, but once you know a star's surface temperature and diameter, you can be confident that it's very close in nature. It's almost identical to other stars that have the same surface temperature and the same diameter. So, they're practically twins. You just have to know a few things about a star, and then you know much more about the star. So our star, there's this classification scheme. The letters seem nonsensical here, but they have a historical basis. Our star, the sun, is a G-type star. It's got a particular surface temperature. It's around 6,000, just under 6,000 kelvins. And we astronomers know that any other star out there that's also a G-type star, so it's got the same surface temperature, puts out the same kind of light, we can be confident that that other star is almost equal in brightness to the sun. That's what I'm getting at here. Once you've identified a star as a G-type star, you can be very confident that it's just as bright as the star, as the sun. Not much brighter and not much less bright. They're practically the same. Now, how are these brightnesses determined? Well, maybe you see what I'm getting at here. Right here in Wikipedia, it's telling us that you could use the inverse square law to determine how bright a star is if you know its distance, or vice versa. So a photometer is a general name for a device for making really precise measurements of the intensity of light coming from some source. So at nighttime, if you pointed this photometer at a particular star, you could measure the intensity of the light coming just from that star if you were blocking out light from all other directions. And I think there's lots of different types of photometers. The Kepler Space Telescope, which was retired a few years ago and is currently orbiting the sun at the same distance we are, it had an onboard photometer. Actually, the whole point of the telescope was to make really precise measurements of the light from various stars as planets orbited those stars and blocked some of the light. There's also something called a bolometer or bolometer. I'm not sure how it's pronounced, but anyway, there are very precise devices for measuring light intensity, especially in astronomy. Okay, so I just looked this up. There are a number of known G-type stars. Here's one, 61 Virginis. And I did a rough calculation to find that this is the intensity of light that we receive from 61 Virginis. Really small, right? That's way smaller than 1.4 kilowatts. And so it's incredible that we can detect such a small number. But again, these things are really, really sensitive. Oops, pardon me. Okay, so if this is the intensity of light that we're receiving from that star, can we figure out how far it is? How far is that star from us? And let's express that distance in light years. Well, there's a couple ways to do that, because I just pointed out that since it's a G5 star, or excuse me, a G-type star, see down here, they're telling us it's a G-type star, we can be confident that its brightness, or the power coming out of that star, is really close to the power of the sun. And that's a number we could look up, or we can do it a different way. So let me point out, this distance is much greater than this distance. Again, not only is it off the screen, if you were going to do this to scale, this distance would have to be something like on the east coast of the United States. The distance from our star system to the next star system is so much greater than our own solar system, it's hard to fathom. Okay, we know that let me clarify what I mean here. I1 is going to be the intensity at the Earth from the sun's light. So I1 is how intense the sun's light is when it reaches us. This is that 1 astronomical unit, 150 million kilometers. I2 will be the intensity of Virginis's, 61 Virginis's light, starlight, by the time it reaches us. And obviously we expect that light to be much less intense because it's way less concentrated being so far from the star. And the reason why I've got the same symbol for the power, the source power in both expressions is because since they're both G-type stars, we can assume that they have the same power output. So why don't we now, let's take the ratio of these two equations because that will eliminate the source power. We don't actually need to look at that number. We can just eliminate it when you take the ratio, excuse me. So what I've done is I've taken the bottom equation and divided it by the top equation. And I find that the ratio, let me put it this way, I have to cough. Okay, so I will express it this way. The ratio of the intensities from these two sources is equal to the reciprocal ratio of the squares of the distances. I think that's a nice way to put it. If you want to know the ratios of the intensities or the ratio of the intensities, just take the ratio of the distances, but the reciprocal, and don't forget to square it. Now, what we're interested in right now is R2. I'd like to know just how far away is this star? Because what we know in the previous slide, I gave you the intensity that we're receiving from that star. We also know the intensity that we're receiving from the sun. We just looked at that number, and we know how far away the sun is, and what we're looking for, excuse me, is how far this other star is. So this is the one unknown in the equation. Let's solve for that unknown. And you can see this eliminates the need to actually look up the luminosity or power output of the sun. So I will plug in some numbers. Is it worth memorizing this? I would say no. Really, you just have to memorize this. This is the one equation amongst these several formulas that I've written down that you need to know. Just take the total source power, divide by the area of that spherical wavefront. And if you know this, you can figure out the rest of this junk anyway. So let me plug in numbers. The distance to the sun was that 150 million kilometers or billion meters. And then be careful. Remember, the intensity I1 is the sun's intensity. I2 is the faraway star's intensity. So since that 1.4 kilowatts per square meter is so much greater than the measly intensity coming from that faraway star, this is an enormous number. Even after you take the square root, it's still going to be a really big number. 10 to the third divided by 10 to the negative 10th, that's 10 to the 13th. When you take the square root of 10 to the 13th, it's still a really big number. Then you still have to multiply by another really big number. And here's how far away that star is. So very simple calculation to figure out how far away these stars are if you happen to know their intensities and if you're confident of what type of star it is. What does this even mean? 10 to the 17th meters? I mean, that's just an unholy number. Let's convert that to something more palpable by comparing it to a light year. So the distance that light travels in 1 year, you can get that by taking how fast it travels in 1 second. This is a number that you will be very familiar with by the end of the semester. And this number right here is the number of seconds in 1 year, which is a number that I just happen to know because I've seen it so many times in these classes. And what you get out is this extraordinarily large number. Let's round it to 10 times 10 to the 15th meters. Now, if you'd like to express that in kilometers, because a kilometer is 1,000 meters, let's use up 3 of these tens, these factors of 10, or I should say powers of 10, and turn this into 10 times 10 to the 12th meters. And that's convenient because 10 to the 12th is a trillion. So we could say that 1 light year is about 10 trillion kilometers. Now that we know that number, let's take our answer for how far away the star is and convert from meters into light years, and we find that it's 27 light years. If I consult Wikipedia, the article about this particular star, I see that the distance is about 28 light years away, which is pretty close. And I'll be totally honest, the only reason it's as close, well, one of the reasons it's as close as it is because all I did was use this number and go in the reverse direction. Knowing that the star is this far away, I used the inverse square law to get the intensity of that starlight from the sun's intensity. I didn't actually look up the intensity of that star's light. But if we did, we would get a very similar number to the 4.5 times 10 to the negative 10th watts per square meter. It's difficult to get star intensities from the Webb in SI units of intensity, watts per square meter, because they're typically listed as what's called an apparent magnitude. It's a logarithmic scale astronomers use, and you would have to convert from that into SI units. Let's do one more example. By the way, don't you just love when you've been talking for 10 minutes only to discover that your mic was muted and you have to do it all over again? That puts me in a great mood. So this time we're talking about sound waves. Let's consider a fictional isotropic sound speaker. I say fictional because have you ever encountered a speaker that's really putting out sound equally in all directions? Most likely, this speaker will concentrate power in the forward direction. Also, we're not taking into account the fact that sound waves experience multiple reflections. So the sound power is going to reflect off the ground. Some of it may be absorbed. So can we really be confident that the 5 watts of electrical power going into the speaker actually result in 5 watts of mechanical power that's conserved on its way out? Doubtful. So this calculation is really just approximate. We could probably improve the accuracy of this model by arguing, well, maybe just the top hemisphere of each of these spherical wavefronts radiates outwards, and the rest of it is merely absorbed by the ground. So we could just cut the power in half and call it 2.5, but I'm going to stick with the 5 watts. And we'd like to know, what's the intensity of the sound waves impinging on this person's eardrum? Now, if you've never done one of these calculations, maybe you don't have a lot of intuition. If you had to guess, maybe you'd come up with a number that's wildly off base. What sort of powers are we familiar with? Well, I pointed out earlier that the human heart has a mechanical power output of something like 2 watts. We know that some light bulbs are 60 watts or 100 watts. Those are the older incandescent bulbs. So should if you imagine the power of a sound wave that's in 1 square meter. Remember, intensity is wattage per square meter. So keeping in mind that the output power, for instance, of a human heart, how much power should be flowing through a 1 meter by 1 meter imaginary square in space? Let's find out. It's a very simple application of the formula. We take the 5 watts, we divide it by the surface area of the giant imaginary sphere that intercepts the person's eardrum, and I find a very small number. So you could put another negative power of 10 and then multiply by 10, and you would have 40 millionths of a watt. What do you call a micro, right? 40 microwatts per square meter. And that tells you that the human ear is very sensitive if it can detect such small intensities. We're going to see that the human ear is capable of detecting intensities much lower even than that. In fact, I think the threshold for hearing is something like 1 trillionth of a watt per square meter. And so the human ear is a very sensitive organ indeed. One further point about that. This number here is rather awkward, is it not? What if this person had a friend with them? Oh, well, that's a silly scenario. If they were being asked, hey, how would you rate the loudness of this sound? Wouldn't it be awkward to say, it's around 0.00004 watts per square meter? It's such a small number. It's inconvenient to work with. Not only is that inconvenient, what's even worse is the fact that the range of sounds you can experience go from as low as 1/trillionth of a watt per square meter all the way up to 1 or 2 watts per square meter. So it's an enormous range. It's awkward to work with numbers like that. So anytime we encounter a range of values that big in physical science or just everyday life, we tend to use a logarithmic scale. And that's what the decibel scale is all about, and we'll save that for another video, but we'll probably use that as an excuse to review logarithms, because you're all supposed to know about logarithms, but I bet you that many of you are kind of weak on that subject. More on that later.